Hi everyone and welcome to this presentation. My name is Virginie Debauche. I'm a PhD student of Professor Raphaël Jungers at UC Louvain, and I'm going to present a joint work with the postdoc Matteo Della Rossa about necessary and sufficient conditions for template-dependent ordering of path-complete Lyapunov methods. So as reflected in the title of this presentation, we focus our work on discrete-time switch dynamical systems whose state evolves according to a finite set of dynamics, and at each time step, the switching signal will determine the current dynamic. So obviously the study of these systems under arbitrary switching is harder than classical ones, and their stability especially remains a challenging question. So several methods could be used, including the Lyapunov theory, for which first you have to choose which type of Lyapunov function you are looking for. So it could be quadratic function or the more complex sum of squares, for instance. And you also have to decide which set of Lyapunov inequalities you want to use. And once you have set up these two parameters, you get a candidate Lyapunov stability certificate for your system. So this formalism leads to a wide range of possibilities. And in this talk, we would like to go one step further, since we want to compare these stability criteria, and we want to investigate the relation with the properties of the Lyapunov function that we are looking for. So this presentation will be conducted in three parts. First, I will recall the main ideas of the path-complete Lyapunov framework and motivate the template-dependent comparison of graphs thanks to the notion of lift. Next, I will present the two main characterization theorems of our paper, and I will finish with a numerical example. But first, let's go back to the Lyapunov theory. As I said, there are many different sets of Lyapunov inequalities that can be used to prove the stability, but we can identify two different classes. So the most intuitive one, and the first which has been introduced in the literature, is the common Lyapunov function, since it amounts to imposing to a single function a decreased behavior along any dynamics of the system. So this tool is quite powerful because the existence of a common Lyapunov function is a necessary and sufficient condition for the stability, but it usually requires to look for complex functions, and the computational cost makes it hard to find one in practice. So the second method, which has been introduced as an alternative to the first one, is a kind of generalization, since we are looking for a multiple Lyapunov function, which means a set of Lyapunov functions whose decreased properties cover every switching sequence. So for instance, this set of four inequalities can be used to prove the stability of a switch system with two modes. But for the sake of simplicity, those sets of inequalities can be translated in terms of graphs where one node will be associated to a Lyapunov function, and each label edge will describe a Lyapunov inequality. So for instance, the common Lyapunov inequalities are encoded by a single node with as many loops as the number of modes. And this example is encoded by a graph with two nodes and four edges, so one per inequality. So this construction actually provides a correspondence between a set of inequalities and a graph. But we still have to be careful, because we know that all the sets of inequalities do not prove the stability, and it is actually the case for the graph. So actually the key property to get a valid stability certificate is the path completeness, which means that one has to be able to create any finite switching sequence with the labels of the edges of the graph. So the path-complete Lyapunov theory is actually a generalization of this framework, since it requires two parameters. First, a path-complete graph, which will describe the Lyapunov inequalities, as we have seen in the previous example, and a template of candidate Lyapunov functions, among which we will look for a solution. And then if you can find a set of Lyapunov function V in the template, such that all the Lyapunov inequalities are satisfied for a graph G and for a switch system F, it means that the pair GV is a path complete Lyapunov function for the system. Or equivalently, we can say that V is admissible for the graph G and the system F. And as expected, it has been proved in 2014 that the path complete Lyapunov function is a sufficient condition for stability. So this framework allows us to play with two parameters. First, a combinatorial one, which is the path complete graph, and an algebraic one, which is the template. And as soon as we change one of these two parameters, we get a different stability criterion. And the question that we tackle here is the comparison of these criteria. So assume, for instance, that you have a switch system and you want to prove that it is stable. And to do that, you have the choice between two path complete graphs, G1 and G2. So intuitively, you will prefer the less conservative one. So formally, we say that G2 is better than G1 with respect to a template V and a switch system F, if and only if, as soon as we have a solution in the template for G1, we have a solution in the template for G2 as well. And we can broaden this definition to a family of switch systems. So in this case, we will say that G2 is better than a graph G1 with respect to a template V and a family F, if the previous implication holds for any system in the family. And similarly, we can say that G2 is better than a graph G1 with respect to a template V, if the previous implication holds for any family of switch systems. And finally, G2 is better than a graph G1 if and only if the previous implication holds for any template of Lyapunov functions. But the question that we tackle is the following. Can we know a priori that a graph is better than another one? And this question has already been answered in 2019 for the general comparison of graphs, since it has been proved to be equivalent to a graph property called the simulation. So formally, a graph G1 simulates a graph G2 if every node of G2 can be associated to one node of G1, such that the edges are preserved. So this relation defines explicitly a relation between the solution of G2 and the solution of G1. So if we take an example, we can see that a simulation relation exists where the node C and E are associated to the node A and the node D and F are associated to the node B. And this means that if there exists a solution VA and VB for the first graph, then there exists a trivial solution for the second graph by taking WC and WE as equal to VA and WD and WF as equal to VB. Unfortunately, in most cases, no simulation relation exists between two path complete graphs, but it is still possible to compare graphs. So in this example, we can prove that there is no simulation relation because the node C2 cannot be associated to any node, but we can still compare them, because it is possible to prove that if VA1 and VB1 are admissible for the first graph G1, then the functions W defined like this are actually admissible for the graph G2, regardless of the switch system. So in terms of inequality, this means that the graph G2 is better than the graph G1 with respect to any template closed under pointwise minimum. So this kind of example have actually motivated the introduction of the notion of lift and its validity with respect to a template. So a lift consists in an operation on graphs such that the lifted graph remains path complete and such that the lifted graph is better than the initial graph with respect to this template. So if you have a valid lift, it means that you have a combinatorial tool to provide better and better graphs. But given two path complete graphs, you can also check whether they could be related by a lift or not. And in this presentation, we have especially defined the mean lift, which extracts from an initial graph the decrease property that results between the minimum of some Lyapunov functions. And as its name suggests, this lift is valid with respect to any template closed under pointwise minimum. And similarly, we can consider the dual lift, which is the max lift, which exploits the pointwise maximum closure properties of a template. And then, inspired by the characterization of the general comparison by the graph property of simulation, we tackle here the same characterization problem, but for the less restrictive ordering relation and for a family of templates that all share the same closure property. So more precisely, we have proved that a graph G2 is better than a graph G1 with respect to any template V closed under pointwise minimum, if and only if the mean lift of G1 that I call G1 min simulates the graph G2. So this result is really similar to the general ordering, but instead here, the simulation includes the lifted graph and not the graph itself. So the proof of this theorem is articulated in 2 steps. First, we prove a key lemma to ensure that given a graph, the existence of a linear switch system and an admissible set of Lyapunov function that satisfies some technical properties. And as a second step, we apply this lemma to G1, and we consider as template the mean closure of the solution V. Then by assumption, we know that there exists a solution for G2 in this template, and this solution defines implicitly the simulation relation between G1 min and G2. So similarly, we can prove the same result for the max lift and the class of template closed under pointwise maximum, and the proof is similar, even if the key lemma here is obtained by duality. So let's finally consider a numerical example with the following linear switch system. And let's assume that we want to approximate the joint spectral radius of this set of matrices, which means the infimum value gamma such that the scaled system is stable. So to this end, we can choose one of the 2 graphs that we have encountered in the previous example. And we have already seen that G1 does not simulate G2, but it's actually possible to prove that G2 does not simulate G1 neither. We have also seen that the function W that are defined like this are admissible for G2, provided that the function VA1 and VB1 are admissible for G1. And this actually translates a simulation relation between G1 min and G2. Similarly, it is possible to prove that G2 min simulates G1. And so this means in practice that if we consider a template which is closed on the minimum, both graphs will provide the same approximation of the JSR. And this is indeed what we see in the result, since if we consider the template of primal copositive norms, both graphs will provide exactly the same approximation. On the other hand, the approximation provided by G1 and G2 with the quadratic template are different. And this can also be explained by the template-dependent ordering, since G1 is actually better than G2 for any template closed under some. So in a nutshell, in this presentation, we have provided a characterization for the template-dependent ordering of path-complete graphs for 2 specific classes of template, which are the template closed under pointwise minimum and maximum. And the proof technique that we have used could be generalizable and relevant for other settings. And these results can actually help the search for a better stability certificate by checking the existence of a simulation relation or not. In the future, we plan to focus on 3 different objectives. So the first one is to get similar results for other operations like the addition or the composition. The second one is to provide a general proof for any abstract operation on Lyapunov function. And the last one is the characterization of similar inequalities for a specific template and for a specific family of systems. So thank you for listening, and do not hesitate if you have any questions. Thanks.